Hello Internet, welcome to another tutorial in the series of digital electronics. We'll discuss full adder today. In the previous tutorial we discussed half adder. A half adder is a combinational circuit that adds 2 bits. On the contrary, a full adder is a logic circuit that can add 3 bits at a time. And the third bit is the carry from a lower column. Now what does that mean? We'll inspect in a moment. Now please understand, in the previous tutorial when we studied half adder, we were concerned about adding 2 bits. For example, if we had a simple case of adding 2 bits, these are 4 different, discrete and altogether not related cases. For example, we have a case where 1 is being added to 0, we have a case where 1 is being added to 1. Similarly, we have a case where 0 is being added to 1, and so on. But those cases are rarely encountered in normal day-to-day routine, because holistically seeing, it makes more sense when the nibbles are added or when the bytes are added. So you'll hardly get a case where you'll be asked to add 2 bits and that's it. So you'll have a bigger picture where, for example, in this picture, if we add 1 and 1, we'll get a sum 0 and a carry 1. Now please understand, when this thing has happened in this bigger picture, we have a condition where 3 bits are needed to be added now. Now this condition where 3 bits are needed to be added now can only be handled by a logic circuit known as a full adder. Now if you look at the definitions, second part, the third bit, which is this one, is the carry from a lower column. So this is referred to as a lower column, and the third bit is a carry from a lower column. So 1, 1, 0 and 1, these 3 bits are being added, and interestingly it'll give a 0 sum and a carry 1. And similarly, when these 3 bits are added, so it will give us 1, 1 and 1 are 3, and binary 3 is written as 1, 1. So we'll get a sum as 1 and a carry as 1 as well. And finally we get a 0 sum and a carry 1. This is the final carry. But you can very well appreciate the fact that a 3-bit adder is needed at this stage, a 3-bit adder is needed at this stage and this stage. The first stage can be dealt with a half adder. So a full adder, full adder, full adder and a half adder can be used at the least significant bits place while adding. So the need for the full adder is completely justified now. So we can have a truth table of possible cases. So let us say we have A and B as 2 bits. The possible bits can be, for example, this is A and this is B, and then it can, these set of bits can encounter some carry, and they'll finally yield us some and carry, which will be the final carry, and this is C in, by the way. Now if you populate this thing, we write down all the cases. For example, we have 2 bits as 0, 0 and they do not have a carry either. Then we have 2 bits to be 0, 0 and a carry from the previous column to be 1. We will have 8 different cases. So I'll write down all the cases. And for these cases, we'll have a sum 0 and a carry 0. We have a sum 1 and a carry 0, sum 1 carry 0, sum 0 and a carry 1, sum 1 carry 0, sum 0 and carry 1, sum 0 and carry 1, and this is the only case where we have a sum as 1 and a carry as 1 also. So this is the final truth table for the full adder. Alright, now once we have the truth table for full adder, just like in any combinational circuit, we need to find out the expression of sum. We need an expression for sum in terms of input, and we need an expression of carry in terms of input. So that can possibly be done by drawing a K map for sum and for carry. So let us draw the K map for sum. So we need to see for each value of a, b, c, for example for 0 0 0 the sum is 0, for 0 0 1 the sum is 1, for 0 1 1 the sum is 0, for 0 1 0 the sum is 1, and for 1 0 0 sum is 1, 1 0 1 the sum is 0, 1 1 1 the sum is 1, and 1 1 0 the sum is 0. So well, this kind of a situation when all the diagonal entries are 1 like this, the simplification of the expression is done by the XORing. So this is A XOR B XOR C. I highly recommend that you watch my videos on K maps to be proficient in solving all this. But for the time being, this is how you find the expression for sum, and similarly for the expression of carry, we again draw a K map, and a K map for 3 variables is an 8 box K map. We know that, so this will be for carry, and I can write this expression for sum here. So for carry, we can see for 0 0 0 the carry is 0, or we can simply write for 0 1 1 the carry is 1, and for 1 0 1 the carry is 1 also, for 1 1 1 the carry is 1, and for 1 1 0 also it is 1. For rest of them it is 0. So we'll need to pair the ones like this, and making pairs of 1 like this will give me an output expression for carry to be equivalent to AB plus BC plus AC, where C is C in. You could write the subscript in like this. So once we have this thing sorted out, then drawing the combinational circuit is not tough, because a full adder will have three inputs, A, B and C in, and it will give us a sum and C out, right? So we'll take three inputs, A, B and C in, and we'll generate the signal AB by an AND gate. We'll generate BC by an AND gate, and AC in by an AND gate also, and finally they are ORed to get carry. And needless to mention here, the sum is pretty simplistic, so taking down all the three inputs to an XOR gate will give me a sum. If you do not have a 3-input XOR gate, you could separately XOR A and B, and then XOR C. So this could give you A XOR B XOR C, or the sum. So this is how a half adder would look like, and it requires 1, 2, 3 AND gates, 2 input AND gates. It requires 1 3-input OR gate, and it requires 1 3-input XOR gate. But the circuit is pretty simple, and the functioning is, the circuit of half adder is pretty simplistic, and the functioning is self-sufficient. It can handle all the situations of additions in digital electronics. So I hope this tutorial on half adder was of help. If you liked the video, give it a thumbs up. That encourages us to make more videos like this. I'll see you in the next one. Goodbye.